still quite high, of the order of 10 to the 10 to the 10 to the 9. So the way it binds, Rose Bengal is one of the much stronger binding agents. So it's coupled very strongly. As a result, we see this. So we also wanted to ask, what is the mechanism? Is it a Foster type or a Dexter type? So, but both have its J integrals. That means the overlap. This is your green one is your cesium lead bromide emission. This one is your rhodamine B absorption. So donor emission, acceptor absorbance. And that is the, when you normalize it, that's the overlap you can use. As I mentioned earlier, if you add some little bit of chloride, you can shift this band further down into higher energy, making this overlap less. So if it is a completely Foster type, without any overlap, you should not see any energy. So this is what we thought. So cesium lead bromide here, if it is a expected energy transfer based on this Foster model, you can see here it would have dropped dramatically as we move the band gap. But we still see this rate constant quite high, even when there is no overlap. So that makes us to conclude that both may be operating. So this is where theory can help us. What type of energy transfer process occurs? What is the origin? What is kind of a interactions is needed to make the efficiency? Again, there are no right now theory to explain how it happens. Again, Ehlers energy theory. Okay, I told you earlier about this upcurrent via TP annihilation. So again, in these cases, they use like lead sulfide nanocrystals to sensitize triplet state, or they also use the PBI3, methyl ammonium, formaldehyde, and iodide. And the idea here is they are trying to generate this rubrine triplet, and they say that through that one they can capture the upconversion. So now the question is, what happens if you decrease the band again? Previously, I showed you this is increasing the band. Now, instead of here, if you move down, what happens? So we'll see if it's a singlet or triplet. So instead of that, so you know, this one cannot dump in energy because this gap now is higher. Cesium and iodide has about 1.9, and your acceptor has. This is the triplet energy. The singlet energy is 2.1. So it cannot dump in singlet, but the triplet is stable. So that's what we wanted to see, and we repeated the same experiment. Again, we did the absorption of Rose Bengal, and here it is the emission of the cesium lead iodide. That's the absorption of cesium lead iodide, and that's the emission of cesium lead iodide. So now you can see here the dye acceptor is at a higher energy compared to your donor. Previously, your cesium lead iodide bromide was here. That's why it transferred singlet. So now it cannot transfer singlet, but you still see the same kind of a quenching beam. So that's what we got. And again, we got about 90% efficiencies based on this quenching plot. So it's very efficient in terms of it. And we were looking for fingerprints, and what sure enough, when we record at a longer time scale, like 2 nanoseconds, we start seeing these features. Sorry. So this is for Rose Bengal, this is isothiocyanate and rhodamine B. We got, earlier we separately characterized the triplet, and we can see the same features that comes in as we see here. So for example, if you have a Rose Bengal triplet, which you see here, there is an absorption down here, and then it goes down and comes up. So it's a very similar behavior. So we are seeing a triplet formation. If you do without the donor, the blank line. We don't see any triplet. So there is not, it's not the origin of direct dye excitation. So that we have confirmed. So now when you start looking the same thing, how fast it is occurring, we recorded the Rose Bengal. Note that again the bleach is now correspond to cesium lead iodide. Your Rose Bengal bleach is in the higher energy region. So, and now we take the slice and plot it versus time. What we see here is again, this is the cesium lead bromide, iodide recovers back, and this growth of this bleach. But if you record now, this should be a second. But if you see this one tail continues, it is not over yet. So we went and took again, these are the other two dyes, behave very similarly. And now we did a longer time scale. Note that this was this should be picoseconds, okay, not nanoseconds. This is picoseconds. So we went to nanosecond. So in the nanosecond, what we saw is this is without Rose Bengal, and this is with Rose Bengal. So you can calculate now how fast is this energy transfer. This is with the isothiocyanate, and this is Rose Bengal. Again, on all cases, when you have the dye, it recovers fast. So if you assume that all this recovery comes from the energy transfer, so we can calculate energy transfer rate by comparing the two, and you get of the order of 10 to the 9. Remember, in the singlet, we got 10 to the 10 to 10 to the 11. So here now, we are getting almost 2 orders of magnitude slower. The triplet energy transfer is slower. So again, comparing this singlet energy transfer rate constant from cesium lead bromide. This is cesium lead iodide. Same dye molecule. So again, by changing the donor from bromide, which is a higher energy, to a lower energy cesium lead iodide, we can decide whether it goes singlet and triplet. So now the question comes why? Why does it do? It's mainly because of kinetics. Although in the case of bromide, both states are available, the faster kinetics takes it over. When you come to iodide, since it cannot transfer singlet, the slower path still dominates and makes it happen. Okay? So doing. So now the question comes is, what happens if you tune in between? Because in the bromide, if you go on adding a little bit of iodide, or in the iodide solution, a little bit of bromide, we can change the band gap. So we always look for simple solutions. So in the case here, we found that if you take a cesium lead bromide and add a small crystal of iodide and stir it, it slowly starts shifting. And you can, because iodide is not soluble, it's very sparingly. So the top solution, you can take it out at different times and get all the different band gap material. Okay. So, so again, you can see here that's the absorption edge and that's the emission corresponding. So we can make all these different ones of this ratio of bromide to iodide. So now we wanted to see how these intermediate states are going to influence, because we are varying from 1.9 to 3 electron volts. The donor, because these are fixed. Let's take the simplest one is 1-to-1, where you have bromide and iodide 50-50. Right? So that comes almost right in the middle of the two peaks. This is a bromide, this is iodide, and this comes. And then what happens is when you do this transient absorption, you can see here, this one recovers faster. This is 1.5, 1.5. And this one is, you can see now it's very close to this one, the band gap. So when we record these kinetics, what we found out was this is the growth of this linkage, and this is the recovery. If you have a singlet only cesium lead bromide, it's very fast. If it is triplet, it is slow. But the one in between is 50-50, you have a fast and a slow. So which means both processes are occurring at this intermediate gap. And again, you can do the same thing. So what we did was we used this bi-exponential kinetics and set this singlet energy transfer and triplet energy transfer constant using the values from here, and then analyze the intermediate state, and the A1 and A2 correspond to the how much fraction of singlet we are getting and how much triplet. And based on that, we can calculate, this is the X different one. So you can see here when is X is equal to 3, that means all bromide, we get 100% singlet. If it is iodide, we get 100. In between, we get both singlet and triplet. So it is nice that we are able to get both of them. So we went ahead and did a series of these band gap materials and got traces, and there is a nice trend you can see here. This is the cesium lead iodide, and when you try to go towards bromide, you see these different components, and we use the same formula. By keeping this constant, we can estimate K. So in this way, we have got both pathways depending upon this band gap. Okay, so this is the final thing here. What we have here is a triplet excited state. When the donor band gap is lower, we see mostly triplet. And as we go down or increase the band gap, the singlet starts taking off. So the triplet pathway goes down, and that's what is. So whenever you have iodide, energetically, this is not feasible. Whereas in between, we can see both pathways. And here, both pathways are possible, but the kinetics is so fast here, it sort of outcompetes the triplet. So that's what we have got it. So again, both energetics and kinetics dictate the energy transfer pathway. So I think this is going to come next month in Jack's this paper. So there we explain this both pathways and how you can get these ones by tuning the band gap. Okay, to summarize this energy transfer, what I told you was cesium lead bromide donor and rhodamine B, etc. Both singlet and triplet can be populated. Yet we observe only singlet energy transfer in the case of cesium lead bromide. The kinetic of singlet energy transfer outcompetes triplet energy transfer. So with the cesium lead iodide donor, we see only triplet. By tuning the band gap, we can modulate the energy. So that is the short story on a energy transfer. So which you normally don't hear much, but if you are doing with any optoelectronics and other materials, you will come across. So this is just a short piece in the sense that how an energy transfer dictates. So now I'm going to switch over to the electron transfer. As mentioned earlier, one of the things that is people are looking is ways to reduce carbon footprint. One way to do is hydrogen, and it is predicted that by 2050, at least 10 to 20% of our energy supply will come from hydrogen, and most of the hydrogen will be generated through water electrolysis, not photocatalysis, water electrolysis. And the reason is there is so much renewable energy excess, especially go to Denmark, they have excess wind energy. They don't know what to do with it. They have to shut down these wind farms. So rather than use it, make it hydrogen and doing it. And you can buy now the stacks of alkaline electrolyzers commercially available. People are putting a lot of these. So eventually come that way. The other one is reduction of CO2 to make some value-added chemicals. So that's where people are doing. So our goal is sort of difficult to probe. See, when you are doing hydrogen reduction or formation or these kind of processes, there are no spectral fingerprints to look into the product or the electron transfer. Again, same thing here. What we use is sort of a probe molecule. The vialogens are very good. They make a nice blue color whenever you reduce. So again, There are a lot of the surface chemistries involved in dictating the electron transfer, but we wanted to see how this redox chemistry. And note that this is a colorless compound. That means the excited state is somewhere around 4 electron volts. So this semiconductor with say 2.5 electron volts cannot transfer energy. So the only way is its redox level. If they are there, then it can dump in electrons. So again, it's the same material. Just now I told you with a molecule it was transferring energy. Now it can transfer electrons to this one. So we want to use this as a probe. And one of the things the cesium lead bromide is it's extremely sensitive to the polar environment. So, but the molecules we are using need to be liquid polar, so that the dilemma. So, but we were able to cap it with a polymethyl methacrylate. Again, making use of photocatalysis to cap by first we ligand exchange with these monomers, and then we photolyze it, and then you got a nice capping. And one of the way you can easily test is add some polar solvent like ethanol. If it is not a good capping, your emission will go down and you will not see anything, or the absorption will change. There is a very little, so you can see here from 0 to 40% ethanol event, and there is a spectrum is very little change, and it dropped a little bit, but it stayed there. The lifetime also remained almost same. So it is highly emissive without undergoing any change. Even in water, it is stable, but it precipitates. So that's how we can do it. So this is one way we try to do this one. Again, we wanted to see how fast the electron transfer. So again, earlier they presented that when you see in a steady state photolysis, you do from minutes to hours, right? But the nice thing about it is people look into the window and claim, okay, that's it. You know, like if I see a with a laser spectroscopy, I say, oh, it occurs in few picoseconds. Somebody goes in nanosecond and says it occurs in nanosecond. So there must be, everybody is right. They are seeing it right, but what they are seeing. So that was the puzzle we wanted to solve. So what we did started with our femtosecond laser system. And you can see here, when there is no methyl violation, as I said earlier, this is cesium lead bromide, you can see its recovery coming back. Then you add a little bit of violation. It's a fast recovery, but the bleach one stays. So the excitonic bleach that you see is representative of a charge separation. Okay? Electron and holes. And as they combine back, it recovers back. So if this bleach remains, means something is remaining. So we did vary the concentration, and sure enough, when there is nothing there, you see this black line. Adding a little bit 0.5 to, so that bleach started increasing, the residual bleach. And we looked into the fingerprint of violation radical that's formed here. And you can see here a sudden rise, and then it stays there. And this is within few picoseconds. So this electron transfer is very fast. We can get from this bleach here, and the formation tells us that within 10 picoseconds, we are taking away electrons from this surface and dumping here. Now the question is, why do we see the bleach? The reason is these holes still remain in this cesium lead bromide. It is not going anywhere, right? So as a result, now we have extended the charge separation. Normally it would have come back very quickly, but now because the electron and here they are coupled, because the violation is very strongly bound to the surface, it is becoming part of it. So if the ligand is bound strongly, it becomes part of it. The wave function extends. So now you have got holes in here. So this gives you more time to do chemistry. Okay, so then what happens is, okay, we can start probing in a longer time scale. Okay, So from picosecond, now we went to nanosecond. Again, you can see here, now this bleach that was there here, this was only 1 nanosecond. So now when you try to do about 30 nanoseconds, this one comes back. That is the back electron transfer. So the electron which is here is trying to interact on this time scale. So you can see here there is a bleach recovery coming with different concentrations. And you can also probe here the violet, which is a product electron, gives you very similar kinetics. So that is this coming back electron transfer. But interestingly, what happens is during that time, either some of them they hop out, like it's an exchange, it's a dynamic thing, right? Or it is just transferring electron to a neighboring one, which is in solution, which is not bound. So that is the residual one absorption we see. Okay, so that is the one we see here, and this gives us the back electron transfer constant. So now, how do you probe this one? Then we do his experiments, steady state photolysis. Okay, in the steady state photolysis, when you have this one, and these are now in seconds. Okay, this is 1,000 seconds, and you can see here that hydrogen radical is formed. So, and again this peak. And now you see here when you study, now I see this growth in minutes. I just told you that it is happening in 10 picosecond, everything is over. Then you will ask why I'm seeing this growth here. This is the net yield. There is a competition between a forward electron transfer, there is a back electron transfer. So until they have these things, this keeps on growing. That is the net product you are seeing. And then this one start, that is this formation gives you. So what happens if you turn off the light? This starts a decay. That is another back electron transfer. So if you know the steady state approximation, the forward rate times the reactant is equal to the back electron transfer times product concentration. So now in this case, there is no forward reaction, only the back electron transfer. So you can easily fit this one and get this value. This is in milliseconds, right? So now, because we know the concentration, we know how much we added and how much is formed. So based on that, we can calculate these values, and this is the net forward electron transfer. So what happens in steady state, you see a plateau because when the rates of the forward and back electron transfer rates same, then you reach a steady state. Doesn't matter how much shining you do, unless you make hydrogen which escapes out. In this case, the product stays there. So just I'm pointing out that back electron transfers are very important to know, and suppressing them can give you a higher yield. If I can slow down this one, I will see a higher yield here. So to sum up, what I showed you was it's a very simple system we started. We started with a hydrogen system in cesium like bromide. When you try to dig in more, you can get more information. So first one is we again use different hydrogen, ethyl hydrogen, heptyl hydrogen, and octyl hydrogen, just to see any chain length dependencies there. But we did not see any chain length dependency. So this is the laser pulse irradiation ultra-fast spectroscopy, where we see these fast rate constants, okay, in the beginning, in the very core. And most of the time, the charge separation is very efficient. It can go even close to 100%. So you can see here. But the net one is always slow. So when you come in trying to do the steady state, now you see a much lower rate constant. And your yields are also lower. So to sum up, what is happening is when you have the semiconductor and electron acceptor, you excite it. The initial electron transfer is very efficient, very fast. And the the product is still bound to the surface. It needs to get out to get stabilized. If it stays there, it recombines back with the rate constant of 10 to the 4 s minus 1. And now, when it some of them it escapes and accumulates, and this one also can go back. Now this is 10 to the minus 3 s minus 1. So that tells you a very complex cycle. So here is another back electron transfer with 10 to the 7 s minus 1. So although it looks very simple, the electron transfer process, you might see people claiming 100% transfer or thing. The fact is that is for the net electron transfer, all these kind of a back electron transfer, which is often ignored, becomes a major player. And depending upon what techniques you use, you get different information. What I've done here is to give you a spectrum from femtosecond all the way into minutes. Different windows you can probe in and try to get a much broader picture. Okay, to summarize, semiconductor nanostructure offer new opportunity design energy conversions with low carbon footprint. Again, they can participate both in energy and electron transfer. Okay? So next time when you think about this nanocrystal and a molecular system, ask yourself the question, how does it decide to transfer energy or electron? So I gave you one possible explanation. Okay? Based on both energy and kinetics. They do determine what pathway it should take. But there may be other explanations too. It's not the only ones. But the way it binds, the way it surface, and the surface interaction donor axis never dictate this one. Strongly bound such as violence and extent quoted in discharge separation. Again, this is to me, there is a very little emphasis on this one and needs to be done. So we have a small group of people working, and the electron transfer was done by Anthony, and energy transfer is done by Vishnu and Akshay. Thank you very much.
Thank you very much, Prashant, for a very interesting talk.
Nice, quite nice. And question that the first part where he was modifying it. In the first part, he was trying to modify the dye, which was a specific functional group, let's say, carboxylic acid.
Yeah, most of the time it's carboxylic acid.
What about the second part, how they are interacting with the?
I think it is because it has this N, right? So it's through the, yeah. So all of the different violations. So that's what we changed the chain line. Still then, didn't make any difference. They all did the same thing. This one, see here, they are very strongly bound. And I think it is part of the, becomes the lattice, some extended, I think. And as a result, it is part of it. I'll tell you, this is not the common thing that residual bleach you see here. Yeah. It is not a common feature. So typically, same thing with the cadmium selenide. We have put a capping with cadmium selenide. We don't see this feature. It just recovers much faster. So this is unique thing. So it took us about 3 students to confirm that what we are seeing. Okay.
Yeah, very interesting talk. I was just wondering, how do you determine that this is a singlet transfer?
So one of the characteristics is in the singlet, you have the fluorescence from the top. That you see. In the triplet, you should be able to see phosphorus. And we tried, unfortunately, it overlaps with this huge emission from the singlet donor. So it gets buried in, and we're not able to. But we did see that transient absorption. Triplet.
I have a question, like how this selection will plays over a role because you have single and triple. It's we're talking about two process like energy transfer and electron transfer. But the electron transfer process is, needs to be, allowed by the conditions selection rule. So is it possible that from the electron transfer also you get simultaneously you get a singlet?
Yeah, again, see the way the electron transfer here occurs mainly because energy transfer cannot occur because the acceptor energy is so high, cannot go up here. But the redox levels are favorable for an electron transfer. So now the question comes is, what are the selection rules? What fraction? See, like for example, molecules can have both singlet and triplet characteristics. So, for example, anthracite, you can get singlet or triplet. So they are characteristics. They are identified level. So here we can sort of assume a singlet energy of the singlet, the semiconductor, because you can see the maximum is the band gap emission. So you can correlate your singlet part with that. But the question is, what is the triplet energy of the semiconductor? I don't know. I mean, people are calling dark excitons, dark triplets, trap states is another one. So all these are possible, but Priya said she is going to tell us.
Yeah, yeah. This is very interesting because when you are mixing the things like the halides,
Yeah.
it is going to make different singlet and triplet states.
Yeah, right, right.
So if you can quantify this,
Again, this is relatively a new field. I'm not saying the energy transfer has been there. Trying to understand these molecule and surface interactions using these excited state interactions. At least I have not seen any theory. Anybody has concluded. But there are theories about your dark excitons and trap emissions. There's always they fight around trap or anything like that. In 2D, you can identify triplet much better. Okay, we have done it. We have put in a 2D naphthalene dye, ammonium dye. There we see the triplet. Clearly see the triplet.
Thank you.
Allow to
Yeah,
ask
yeah, go ahead.
more.
Yeah, of course.
Okay, so suppose I have that when
You
you are
bring it.
when
So
you
that
are
others can the back
taking
end.
the singlet and triplet, when the changes the structure.
No, because see, when you exchange the halide, it's the same thing. So we stir with iodine. So it's a very sparingly soluble. So it just kicks out the bromide and get iodine. And all the ligands, everything is in there. Nothing changes.
So when you're going through the process, you think you can capture in the intermediate state if it's a change in local symmetry.
No, this is, it's again, it's a very easy experiment. You make the cesium electrode solution, throw 1 or 2 crystals of potassium iodide. And the potassium iodide is not soluble in solvent, but it's sparingly soluble. In the sense like you'll release slowly some iodide ions. And as the iodide, it's a very slow process. You have to do like in hours to get all these different. So it gives you a window. I wish I had we have captured the video, show how the emission changes with time. And then the nice thing is you can just take a supernatant and centrifuge it out, and that one stays exactly. You can store it and use it.
If there are no further questions, we thank Prashant for a very nice. You'll need it, definitely. There's some tea waiting outside.
Okay, okay. Thank you. Thanks for the opportunity to share some of it. This was the children exam coming in January.
Okay, and if it's
Yeah.
no, ma'am. You can you come.